Hello, good morning, and welcome back to Refactoring Bitcoin. I think the time is right that we start covering C++ basics. So today I want to introduce you to classes in C++. Why do we have classes? To answer that, I want to answer another question first. How do we write complex software in any language? And on the highest level, the answer is almost trivial. Of course, we use a divide and conquer approach where we split the large complex problem into smaller problems. We decompose a large system into small components of manageable complexity. Components that we can reason about, that we can verify in isolation. And then once we have those verified components, we can compose them into a larger system, and we're done. And this sounds straightforward, but it doesn't work like this in practice. And the reason why it doesn't work, the key word here is dependencies. Um, when we have components that are truly independent, it means they also do not compose well. If you want to compose a larger system from components, then those components need to interact with each other. But if the components interact with each other's implementation details, then it's a single component is hard to reason about. To understand a single component, you have to understand all the components and how the other components are implemented that they interact with. It's also easy to it's hard to test because testing a single component requires all the other components, so you cannot test the component in isolation. It's also the build is slow if dependencies are too tightly coupled, because if the component is hard to understand for the machine, it's also hard to understand for the compiler. Compiler needs a lot of information, right? For example, needs to parse a lot of header files because each header file includes so many other header files. And not only the initial build is slow, also the rebuild is slow. If you make a component in one place and you want to rebuild, and the whole system needs to rebuild. And not only compiling the change, also making the change in the first place is tricky. If you want to make a single change, and making a change requires this other change, and this other change requires further changes. So if you would just want to fix a tiny little thing, make a single tiny little change that requires so many other changes, so you have a PR in the end that is hard to review. So, and the last two bullet points here highlighted something else. Another keyword here that is change. So this is only a problem if changes are actually made. So the question is, should we avoid changes maybe? And I want to answer that with a clear no. It's called software for a reason. Software is called software because it's meant to be easy to change. I like this quote here very much. We don't solve a problem, we approximate a solution. That means our understanding of the problem evolves while doing the development. Also, while doing development, we may get new requirements, or we learn new things. We learn better ways to structure the program. Also, the programming language evolves, of course. So there's always a need for making changes in the code. And that's a good thing, right? So this is the advantage of software over hardware. But if making changes is complicated, then the software is no longer soft; it becomes hard. Okay, and the key here, the key to the solution is abstraction. Abstraction means separating what something does from how it does it. So if a component foo depends on another component bar, it should only depend on an interface. So bar should provide an abstraction over the implementation details in such a way that bar's implementation details can be changed without affecting the interface of bar, so that foo is not affected from the implementation details of bar. If you do that, then our system as a whole becomes easier to reason about because you can now look at a component in isolation. You still have to understand the components it interacts with, but only until the interface boundary. You don't need to know the implementation details of that. It's also easier to test because now you can mock the other objects, the dependencies it has. Um, of course, I say here easier. It's not easy. It's still complicated, right? Because we still components still have dependencies. There are other ways we can reduce the number of dependencies that makes it even more easier. But just the abstraction itself makes it easier to reason about, easier to test. It also makes the build faster because the compiler can. I mean, if the system is complicated for humans to understand, it's also complicated for machines. So the compiler has to do a lot of work um, building the project. And if we have abstraction, it's easier for the compiler and therefore faster. Also, the rebuild is faster. If you make a single change in an implementation, then very often only the compilation unit for that implementation needs to recompile, and the rest of the system just needs to relink. And sometimes even just restart, not even needs to relink. It's easier to refactor, of course. You can make changes in isolation. Changes do not ripple through the system if you have abstraction. But I want to make it very clear that by abstraction, I don't mean polymorphism. So this is not about abstract base classes and virtual functions. No, no. This is just separating the declaration from the implementation. And this is possible in C. In C, we have the perfect mechanism for abstraction. This is the opaque pointer pattern. And it is perfect in the sense that it's absolute. So the implementation details of a component are truly hidden. So we see here this example of a transaction type. We have this forward declaration of the struct. This is an incomplete type. And then we have a tx create function, which can be seen as a constructor. We have tx destroy, which can be seen as a destructor. And then we have those other functions, tx num inputs, inputs add, tx num outputs, and tx num outputs add. Those can be considered member functions. And a client that invokes the tx create function creates a gets a pointer to a transaction object. But the client cannot do anything with that pointer. The client cannot dereference the pointer and look what's inside an abstraction. The only thing that the client can do is pass the pointer to one of those other functions. Okay, so this is it's really good abstraction, makes the code faster to compile and easier to change. But it comes with a cost. Because since the abstraction is absolute, so things are truly hidden. The compiler does not. The compiler that compiles the client code does not does not know the size of the object, so it cannot be put on the stack. Each individual object needs to be allocated on the heap. So if you want to have an array or a sequence of transactions, then each one of those needs to be individually heap allocated. So this causes memory fragmentation. And also accessing a transaction, each member access requires a pointer interaction. And because of memory fragmentation, that can lead to cache misses. So this is just makes the whole thing slow. It's also error prone because the lifetime management is manual. When a transaction is no longer needed, it needs to be deallocated by explicitly calling this, how is it called, tx destroy function. And so this is error prone because people may forget, but this is not the real problem. The much bigger problem is because programmers are lazy, they don't want to call this explicitly, so they invent other solutions built on top, things like garbage collection or reference counting, which then brings in additional overhead, and those hacks, those workarounds, they also have the other problem that if the state that is shared here is mutable, so we have shared mutable state, which then is the problem if you have the same object used in two different places. The one place, the client assumes that the object is immutable, because the client does not intend to change it, but some other client has a reference or the pointer to the same object and makes a modification, and then the first client observes the modification in an unexpected way. This is what we call spooky action at a distance. This is very hard to track down where the modification actually comes from. This is very hard to debug. So when performance is a concern and abstraction is a concern, so if you have a complex system, uh, and so you need abstraction, but you also want to have performance, then C is not a good choice, because you always have the trade-off between abstraction and performance. And C++ key idea is never compromise performance. So C++ gives another way to look at abstraction. It separates the visibility from accessibility. So here on this slide, we have also a transaction type with the same functions. Basically, we have a constructor, we have member functions. The destructor is not shown here, because in C++ destructors are implicit. If you don't provide one, there is provided for you. But the key difference here is that the implementation detail is visible. It's just not accessible. It's hidden behind, or it's it's not hidden. It's visible, but it's behind this accessibility specification here after the private keyword. And you see here down below how clients are supposed to use this. They simply create a transaction by passing the raw bytes here in the constructor, and put an object on the stack. So there's no new keyword here. If this was created with the new keywords, then it would be allocated on the heap. That would defeat the complete purpose. So and it's also interesting here that the implementation detail, because it's behind an abstraction, can be changed. So we are not required to put the implementation directly in the private section. We can use the indirection with the opaque pointer, just like in C. But since this is now behind an abstraction itself, so the fact whether we use indirection or not is inside the private section. So that means we are free to change it. We start with an implementation where we hide the details, and later when we know how the class is supposed to look like, when it's changed less often, then we can change the implementation to directly be visible but still not accessible. Okay, so what are the things that C++ adds to C regarding classes? So those features are very old. They were the first features of C++ that were added to C back when the language was still called C with classes. So the thing that C++ adds are member functions. Yeah? C only has data members inside structs, and in C++ you can also have functions inside a struct. Then we have those access specifiers, public, private, and protected. C++ also adds inheritance and new keywords like class, this, and friend. So we will look at what those keywords do, and we also need to look at guidelines. So once we understand what these keywords are, we want to understand where to use them. So what are those keywords? So what members should be private, what should be protected, what should be public. Also, when should we use a struct or when should we use a class? And you may remember that I said that the non-member functions of a class also belong to the class. So you want to understand, you want to know when should a function actually be a member function and when should it be a non-member function. So let's dive in. The access specifiers, they control the access, right? There are three keywords. The access specifier public declares the things that follow as accessible from anywhere. Everything in the private section is accessible only by the class itself and its friends. So you can declare other classes and other functions as friends of a class. That means it can only also access the private members. And there's also protected, which is restricts the access to the class itself plus its derived classes. And then the default access specifier for class is private, and for struct it's public. And this is the only difference between class and struct. So let's look at some example code. So this is a struct in C. It has two members, and they are both data members, of course, because C only has data members. But in C++, what we can do now is we can add member functions. So let me show here. I add two member functions, gets data and sets data. And the gets data function just returns the data. And the sets data function sets the data after checking a precondition. And you see the syntax here. This is the pointer that to access the data. So the next thing that we add in C++ is the keyword for the access specifier. So we make the access of the data private, which now means the only way to modify that data member is through this setData function, which of course means the only way, so there's no way around this precondition check here. And we now have implemented an invariant that the state of the class itself always satisfies the precondition check here of the value that was set through the setData function. And all the other members, that means the bar data member and also the get data and set data member functions, they are publicly accessible, right? There's no access specifier for them, but since foo is a struct and the default access specifier for structs is public, so those members are public, of course. The first data member here, bar, this is another struct, which is a common pattern in C to have in a struct another struct as the first data member. This is implemented as some kind of inheritance because the memory layout of the structure guarantees that if it's at the end, that means the class foo and the class bar, they point to the same address. So when we have a pointer to bar and we know that the thing is actually foo, that means we can cast the pointer to bar to a pointer to foo, and then, for example, on that pointer, call the gets data or sets data function. And in C++, we have a nicer syntax to do exactly the same. This is just placing bar after the colon. Okay, and this is now also using public inheritance because since foo is a struct and the default access specifier is public for structs, that means bar is publicly inherited. Foo is publicly inherited from bar. And if we want to change that now into a class, so we replace the struct keyword with class, and we also explicitly specify the access specifier, we now explicitly inherit publicly from bar, and we also explicitly mark the accessor functions as public. And the default access for structs is private. Therefore, we can also actually move the data member to the top, where it's now it doesn't have an explicit specifier. It uses the default one, which is private for classes. So this allows you to save one line. Whether that is a good idea or not is a matter of taste. Some projects have guidelines that prefer this approach. Other projects have guidelines to avoid this approach because they prefer to be explicit, to explicitly specify the access of each level, right? Public, and then very often also start with public, then the protected members and the private stuff in the end, because the idea is that you read a class from top to bottom. You want to understand the public interface first and later go to the details at the end. So this is basically the whole mechanism that classes provide. But now we want to know about guidelines. When should we actually use which? And when I ask the question, when should data members be public? When should they be private? When should they be protected? The answer I often get is data members should be public when they need to be accessed from outside the class. But this is not a guideline, right? This is just repeating the mechanism. Of course, data members that are public can be accessed from outside the class, but we want to know, when is that a good idea? When is it a good idea to access the data member directly outside the class? And of course, we just heard in the introduction, the whole idea is abstraction. And therefore, of course, we want abstraction. So the answer, when should a data member be public, is never. Okay, it's also easier to remember the guideline. When should they be private? Always. And when should they be protected? The answer is also never. So when you need, for example, when you have a data member that should be read accessed from everywhere, but it should only have write access. It should only give write access to other to derived classes. Then of course give a setter function, give an accessor function for derived classes. The idea of abstraction is that other classes are implemented against an interface of your class, and of course derived classes are other classes, so they should be implemented against the protected interface of your class and not against the private implementation. Good. Then you might ask, but does it really matter? So if I have a class, I give it a data member, I give it a getter and a setter function. Does it make a difference whether I just make it public? And the answer is yes, it makes a difference for multiple reasons. Number one, you want to implement invariants, and maybe you don't, you cannot think of invariants yet, but maybe you realize them later. So if you want to add a precondition, if you want to check a precondition, then the easiest way is to do that in an accessor function. It's very hard if you leak the implementation detail, leak the member, other clients access it directly, and you realize that you want to establish an invariant actually, or make sure that only certain values can be set. It's now necessary to have this check across the code base, and with a setter function, you have it in a single place. Also, you want to control who reads and who writes. It's actually rarely the same client, very often you have clients that produce data, pass the objects to some other client, and the client then consumes the data. Um, and if you want, for example, if you want to measure how often is it accessed and how often is it just set, then it's much easier if you have a function where you can hook into. Also, you want to reserve the right to make non-breaking changes. And this can be done with accessor function. It's also important that you do not leak too many implementation details in the accessor function. So imagine you have a data member of a vector. The getter function should not return the vector by const reference. Because if you return a reference, you're leaking the implementation detail that the thing exists, right? You can only return a reference if the object exists somewhere. So when you return a vector by const reference, you still have the flexibility to change whether that vector is stored directly or indirectly, but it has to be a vector of that exact type. But if you instead return a span instead of a vector in the getter function, then you have now the flexibility. You have reserved the flexibility to change the container. You still leak the information that it's a container that stores the element contiguously, but there are other ways, right? So with a with an any view, you can actually decide how much information you want to leak, but a span is also already much better than a vector directly. And also another reason is why you should not focus on those getters and setters too much. So very often, so the in practice, this triple, the getter setter member triple, is actually quite rare. While we are at vector, the example here, when we look at the member functions of the vector, of course it has getters for the size and the capacity, but there is no setter for the size or a setter for the capacity, because setting the size has other side effects. So if you set the size of a vector, it also potentially reallocates and has effects on the capacity, and also changing the capacity may also reallocate. So in practice, it's actually rare to have the triple getter setter member. Okay, so now we understand that data members should always be private and we should provide accessor functions. So the question remains, when should we actually use a class and when should we use a struct? The C++ core guidelines, they mention this in two places. There is C2. It says use class if the class has an invariant and use struct if the data members can vary independently. I'm not happy with that guideline, but I will show you why. And the second guideline is use class rather than struct if any member is non-public. So I just told you that data members should always be private. So what this means here is that always use class if you have data members, right? But there are exceptions, which I will also want to show. So first we look at the first guideline here. The C++ standard library has a type called pair. It's a templated struct. It's a struct template with two template arguments, and it just has data members of the first and the second template argument. So it does not have an invariant, and the data members can vary independently. And it's a struct. It follows the guideline from the C++ core guidelines. But was that a good choice? And I would say no, okay, because there is this boost library called compressed pair, which shows a potential alternative, how pair could be implemented instead. And this uses empty base optimization. So imagine when you have a type, a struct or a class in C++ that does not have any data members, then it still has a non-zero size. Because if it had a size of 0 and you want to put the elements of that type into an array, and if each element has a size of 0, that means all the elements in the array would have the same address. And this is not allowed. And therefore, so we want each object to have a unique address, and therefore even a struct with 0 data members has a non-zero size. But when you inherit from a type that does not have any data members, then, and if the derived type has data members, then we can say that the base class at least does not contribute to the size. This is what we call empty base optimization. And this was discovered probably after pair was standardized. So the idea is we could actually use empty base optimization for pair to avoid, to reduce the size, reduce the overhead. But since we leaked the implementation details of the pair, since we leaked the fact that those have to be members, we have lost the flexibility to make that optimization. So it would have been better if pair was not designed like this, if pair was designed with private data members and accessor functions, and then once the empty base optimization technique was discovered, then the implementation could have been changed. The data members could have been replaced by inheritance, and without affecting the API. But since it was designed like this, the implementation, so the ability was lost. It was not reserved. So this probably was a mistake, and we learned from that mistake. And there's another client, and there's another type in the C++ standard library that it also does not have invariants, and the members can vary independently. That's a tuple. And yet, tuple is not a struct, it's a class, and the data members are private. So it does not really follow the C++ core guideline C2, and it's probably a good idea that you also do not follow it, but follow instead my recommendation. Always make data members private. It's also easier to remember if you do not have exceptions to that guideline. So, the other question is, when should we use struct and when should we use class? And my recommendation would be use struct even with public data members when you already are inside an abstraction. So inside the private section of a class, you can declare a struct because the data members can only be accessed by the class itself. So you don't need to have this double abstraction. It does not gain anything. It does not provide additional flexibility to make changes. So there, it's a good idea to just use a struct and without any explicit access specifiers internally. So, which brings me to the last question. When should we actually use a member and when should a function be a non-member function? But this requires a little bit more explanation, so I want to make this in a separate video. So that was it for today. Bye. Thanks for watching.